Okay, our next speaker is James Gillin from Kansas. He's going to tell us about Eulerian numbers and relations to number triangles and infinite series.
Okay. Hi, my name is James Gillin. I'm from Washburn University studying pure math. And today I'll be talking about the Eulerian numbers, number triangles, and infinite series and kind of the relationship between these three things. Now, all of this started from my problem solving class when I was tasked with finding probabilities of an exploding die, which is a die where if you assign one of the sides to it, where if you roll that number, then you have to re-roll again and keep adding to it if you keep hitting that number and keep re-rolling. And in those probabilities, you have to calculate a certain infinite series, and that one being the series I to the n, the infinite series I to the n, x to the I for all natural numbers n. And when I was looking at this, I was thinking, how should I approach this problem? You know, what are some steps I could think about to solve this? And I also thought, where do I begin? And thinking about this, I thought, what are some infinite series that I know really well? And the first one that popped to mind were geometric series. Now, this is a really good picture that shows a picture proof of the convergence of the infinite series 1/4 to the n, but without with the first term removed. So you start at n equals 1 instead of 0. And if you look at the L shape of this picture and look at the pink square area, you see that's 1/3 of the L shape. And if you keep going down the line, so let's look at the first area, that's equal to a half times a half, which is a fourth, which is the first term. Then the next square is a fourth times a fourth, or 4 squared, that's the second term. And then the third area is 1/4 cubed, the third term. And going all the way down, we see visually that this is a third, and that's what it converges to. And so using that and the general formula for the geometric series where the absolute value of x is less than 1 is for it to converge to that equals a over 1 minus x. And I thought this is a promising starting point for me. This looks good. And I thought, what clues from this and other versions of the problem that are simpler can I look at to give me inspiration to what kind of pattern is generated? So I did that, and I first calculated the first series where n equals 1 on the original expression. So that's S, and I called it S1, and it's I to the x, ix to the I. And first I wrote out all the terms. And since we know that this infinite series converges using the ratio tests, and for the x's that converge in the ratio tests, then we can separate the terms. And so I separated different x's, powers of x's, and added and subtracted 1, which is the same as 0. And then looked at this blue portion that I highlighted, and you'll notice that that is a geometric series with a equals 1. So I just replaced that with s since we know what it equals. And then factoring out an x from the right side, this portion by the x, it's the same as the terms from the original S1 series. So we just rename that S1. And then going through the algebra and substituting 1 over 1 minus x for s, we get that S1 equals x over 1 minus x to the power of 2. And then I took that and I said, hey, let's look at the n equals 2 and n equals 3 case. So I calculated all those series and came out with this. Now I want you to pause and think, what patterns do I see in these expressions? Now, one that immediately comes to mind is in the denominator, there seems to always be a power of 1 minus x, and specifically a power of 1 more than the I is raised to. So I thought that's one pattern I noticed, but is there a pattern in the numerator that I could find? And it looks like there's a polynomial, but the coefficients seem to be really random. Like, what is the pattern there? So what I looked for inspiration was Pascal's triangle. And hopefully all of us know that the entries in Pascal's triangle generated from taking the entry to the left and the entry to the right above the given entry and adding them together. And that can also be known as the binomial theorem, where each entry in Pascal's triangle is just the coefficients to the binomial. And it can also be written as n choose k combinations. And then with all of that, and also the binomial theorem is just that written out. So with all of that as a reference point, I again looked at the numerator of each expression and I noticed a pattern, and immediately my hand, just without knowing, just wrote down the numbers. They just came to my head instantly when I looked at this pattern. And so I came up with a guess for the next one, S4. And I guessed that it was x to the fourth plus 11x cubed plus 11x squared plus x over 1 minus x to the fifth. And through very tedious calculations by hand, I've turned out it was correct. So I was really excited from this. But this begs the question, how did I think of this? What pattern did I notice? Well, I made a number triangle, of course, and I called it my number triangle. And you'll notice the main property of this is that each row adds to a factorial number. So the first row is just 1 factorial. Second one, 1 plus 1 is 2 factorial. 1 plus 4 plus 1 is 6, which is 3 factorial. 1 plus 11 plus 11 plus 1 is 24, which is 4 factorial, and so on, all the way down the line. Now, it's important to note that I could have just picked any numbers, whatever that could add to a factorial number for each row. That doesn't prove anything. There's a pattern that I saw with the other coefficients that came up with a formula to generate these entries, which will be important later, important to know. So the pattern that I saw was that first thing I did was the first and last entry were always just a 1. That's just how that is. But then to get the other entries, what you do is you look at the entries to the left and right of the row above, like Pascal's, and add them together. But you also have to add the factorial of the row before it, which can be written as g of nk equals g of n minus 1 k minus 1 plus g of n minus 1 k plus n minus 1 factorial. So it's like Pascal's, you just have another thing to add to it. And this is a little animation that demonstrates the formula to generate it. So let's say we want to calculate 11. So we take entry to the left, 1, entry to the right, 4, add them together, look at the row before and the factorial of it, which is 3 factorial, take that, add it together, take the whole thing, and we get 1 plus 4 plus 6, which is 3 factorial, equals 11. Now, did I finally solve this problem? Were these the correct coefficients I needed in the polynomial to solve this? Well, spoiler alert, unfortunately, no. This wasn't correct. Thumbs down on that. So, should I give up? Is this it? No, I don't give up that easily. So, but what went wrong exactly? So using my triangle, I looked at the 5th row and said, this is my guess for the 5th series. But through another tedious calculation, it was incorrect. But thankfully, I didn't give up, and I presented all this findings to a professor at the University of Kansas, and his name is Jeremy Martin, and he gave me some insight that finally led to the solution. And the insight he gave me was something called the Eulerian numbers. And in combinatorics, they are the number of permutations from the numbers 1 to n with k descents, and descents being the number of elements that are smaller than the previous one. So for example, these are all the 6 permutations of the numbers 1 to 3. And looking at them, they can be represented in nodes and lines. And each time you see a negative slope, you know that's a descent. And so we can divide these up. So we have 1 0 descent, 4 1 descents, and 1 with 2 descents. And it's pretty obvious from this that you'll always have one that has no descents and one that has n minus 1 descents, which are the no 0 descents are the straight line up, and minus 1 descents are the straight line down. And using this, but it's harder to get the numbers inside. So there's luckily a recursive formula to generate the other entries. And to calculate this, use this recursive formula, which is t of nk equals n minus k times t of n minus 1 k minus 1 plus k plus 1 t of n minus 1 k. And the proof of this formula involves looking at an arbitrary permutation and removing one element from it and looking at the digits to the left and right of it and comparing their values and noticing that either the descents stay the same or decrease by 1. And from those, you get these combinations. And then Eulerian numbers also happen to have their own number triangle called Euler's triangle, which was studied by Euler. And here it is. And you'll notice that it shares similar properties with Pascal's and my triangle. The one being each row is equal to a factorial number. And in Pascal's, each row is equal to 2 to the power. And then also the first 4 rows are identical to mine, so no wonder I got confused. So then this is a picture that helps us grasp the recursive formula. So if you notice in the top left, what you do is you look at the 2 arrows. The one on the left is n minus k, that's that term. You take that with the note on the left, which is n minus 1, k minus 1, multiply it together. And then on the right, you take k plus 1 and the n minus 1 k term, multiply it together, and then add them together and put it into that term. I also have an animation for that. Let's look at the 26 with 1 and 11 to the left and right. So we take n minus k, which is 4. And we take k plus 1, which is 2. And then we multiply the 1 and the 4. Multiply the 2 and 11. Take those results and add it to get 26. And it looks like that. So now, fixing the mistake, I took the 5th row of Euler's triangle into this formula and followed the powers of 1 minus x in the denominator and checked this one, and this turned out to be the correct expression. So now I thought, finally, I have a pattern to do this. And so I decided to put it all together into a theorem. And so the closed form solution to the original problem for all natural numbers n is I to the n, x to the I equals the sum of k equals 0 to n minus 1 of t of nk, x to the k plus 1 over 1 minus x to the n plus 1. And where t of nk are the Eulerian numbers. And this is proven using induction and the recursive formula to generate Eulerian numbers. So you prove it for a base case, and then you prove it for the n plus 1 case. And you use the recursive formula and also taking a derivative and multiplying by x. And it's in my paper. It's not too complicated. It's just an induction proof. But I want to thank Professor Porta for advising me on this, Professor Cook for helping me with the slides, Professor Jeremy Martin from the University of Kansas for helping me with the insight to solve this, and Professor Wagner for introducing me to Professor Martin. And I want to thank Malloy University for hosting me. And here are some references for the Eulerian numbers. So thank you.
Question for a speaker.
Okay, so your my triangle.
Yeah.
Okay, something that's yours, right? And that came from observation.
Well, yeah, I had it as Gillin's triangle, but I guess it didn't update in the slide.
Basically, it's your triangle.
Yeah, yeah.
Are there any properties? They're kind of like isolated, just focus on that triangle. When you observe any properties, or other properties that can often.
Not exactly. I haven't looked at it like too much yet, but I do want to, that's where I want to take this further, is looking at my triangle and Euler's triangle and seeing other properties that maybe they share some. And I just want to go further with it, but I don't have an answer to that yet.
And then I guess the follow-up is that you mentioned that, like, so when you start playing with it, right? So I think you addressed the question, how did I get to the triangles? So, right. So how did you get to the triangle? Because I'm looking at
Yeah.
Not a triangle.
Yeah, well, I just looked at the coefficients of the polynomials and the numerators, and I just immediately thought of binomial theorem and Pascal's triangle. Yeah, so I just thought maybe this has a number triangle too. Yeah.
Thank you, speaker. We're gonna have a little bit of a break, and then we're gonna 3:20. There's gonna be a workshop in KC 015, so on the 0th floor.
And so it won't be this building, but we'll help you.
Hey, can I get a show of hands? How many of you all are gonna go into the city after the conference ends tonight? I want to go on like an expedition in the city. I was just curious if who's going. Okay, I just. What? You guys like? I'll go. Like if we want to go in a group or something. If you guys let me tag along, and it's just me. I don't know. I want to hit up. I have a passion for ping pong, but if we can make like a group, it doesn't just have to be that. Obviously, if you guys are more comfortable doing that, you can. I don't know. I'm willing to go, but I just want to put that out there. It's New York. Yeah. So I was gonna go by myself, but I figured if anyone else wanted to go, we could coordinate something. So. Epic match. Absolutely. No, it's actually a 20-minute break because sorry, it's 3:20, so it's 20 minutes. So we want to. That's not. Where is what? It's